conferences as a program committee member and has done a lot of good work. He's a senior professor, so I'll let him speak.
Okay, thanks, Ruta. Sorry for curtailing your lunch break. Okay, so as Ruta said, I'll be talking about routing games and some new perspectives and the challenges that arise in dealing with these new perspectives. So by new perspectives, I mean some things that have come up in the last, I don't know, maybe 5-6 years, or even more recent than that. And this is mostly based on joint work with Umang, who's there in the audience, Katrina Leggett, Leonard Schulman, Young-Kun Ko, and Yu Chang. And I should give a special acknowledgement to Umang because for sharing his slides with me. This is many of the slides that I'm going to show here are like shameless ripoffs on what Umang shared with me. Right? So hopefully Umang doesn't mind, especially since I acknowledged him. And I'll start off with one other, confession that so this was my goal to talk about both query models and signaling. But as I was preparing the slides, I realized that there is quite a bit that I have to say about query models. So I may not really get to signaling. I may have only a little bit of time to get about signaling. It's not that I don't think that signaling is interesting. I think it's quite interesting, but I will probably be covering much more of query models and may not really get to signaling. I'm most happy to talk to any of you guys offline about signaling. It just may not happen during this talk. Okay. So and also this talk is meant to be self-contained. So I'm not going to assume any background knowledge in routing games. We will. They're fairly elementary, so it's not hard to cover what I need about routing games. And so feel free to ask me at any point of time questions if something is unclear. I mean, this is meant to be a tutorial. I think we have enough time, so feel free to ask questions. Right, so what are routing games? Routing games are basically a model for traffic networks. So they're a way of modeling traffic in networks, and when I think of this, the evocative image, the image that I always have in mind is that of road networks and traffic in road networks, right? Something that we all experience pretty much on a daily basis. So that's one of the things that routing games model. But the same kind of model turns out to deal with other kinds of networks where traffic is routed. And for example, they could be data networks where packets are being routed along links. Or it could pertain to a scheduling system involving assigning jobs to machines in data centers, right? So all of those are routing games are a versatile model that can capture all of these. So here are some common features across all these examples. So there's some set of resources that are shared across various players. The players are competing for these resources. And the other sort of defining characteristic is that nobody is really dictating how players use these resources. So there's no sort of designer that tells me that, okay, you have to follow this route, right? The players are naturally competing and deciding for themselves what routes they want to take. They have their own self-interest in mind. They're not usually malicious, but they are self-interested. They care about their own utility, right? There's no sort of global objective that they're trying to optimize, right? And so this naturally calls for having a game theoretic model for traffic in networks, and that's exactly what routing games are. Routing games are we're going to use aspects of game theory to model this kind of phenomenon, and the point is that by modeling this kind of phenomenon using latent game theory, which is more apt to deal with situations where there's a natural competition, we seek to analyze how competition affects traffic in these kinds of networks. Right. So here's a mathematical model for routing games, right? So let's say I have this very simple example. There are two links. So think of these as two roads to get from one source S to a destination T, there's these functions here. So the function is indicating what is the per unit delay if X traffic is routed on that edge, right? So this is saying that, for example, if X is 0.5, then those 0.5 units of traffic that are going along the bottom link are going to experience a delay of 2 times 0.5, which is 1, right? On top link, it's constant function 1, so whatever, regardless of the amount of traffic that's routed, there's going to be a constant delay of 1, right? And this one here is telling me what's the traffic, what's the volume of traffic that's going from the source to the sink, from S to T, right? So we're going to make an assumption here, which is not necessary, but it by far gives rise to the cleanest mathematical model. So the assumption that we're going to make is that an individual player controls infinitesimal amount of traffic. So an individual player is going to have a negligible effect on things. It's only aggregate traffic that's going to have any effect on things, right? So this is kind of the thing that, when you have a large volume of users, a single user has negligible effect. That's what we're trying to model. So if you think of packets, an individual packet, which is maybe some bytes, a few bytes, compared to the volume of traffic, which is some kilobytes or megabytes, that's the kind of phenomenon that we're modeling. So each player is self-interested. It's choosing a route from S to T. In this case, there are 2 possible choices. So the aggregate of these routes give me a flow, and it's a flow of volume 1. And now I want to reason what is a stable outcome for this flow. Yes? How do I make? So this is, I'm assuming that that's what's given to me. So this is, so think of this as a very wide road where, regardless of the traffic, up to within some bounds, the constant delay, and here this is a narrow congested road, so the delay increases with the volume of traffic. But I'm not talking about how we model these latency functions. We're just going to say that these delay functions are given to us as part of the input. Okay, so I want to reason about what's a stable outcome. So this model where each individual player is controlling an extremely small amount of traffic, negligible amount of traffic, is called non-atomic routing, right? So let's say that half of the traffic chose the first link, chose the top link, right? So I want to reason about. So let's say that was, I knew that this happened in a stable outcome. I want to reason about how the remaining half unit of traffic gets routed. Right? So one option is that, so let's look at a few different options. So let's say that all the half unit got routed on the top link. Now would this be a stable outcome? It's not going to be a stable outcome, and it's not hard to reason why. Because, there's zero amount of traffic, right? So right now, all this one unit of traffic on the top is seeing this bottom link as being an extremely attractive link, because if they switch to the bottom link, then their delay is going to be zero essentially. If an epsilon amount switches to the bottom link, then the delay is going to be 2 epsilon. So if epsilon is small, that's going to be better than what they're experiencing. So the guys on the top have an incentive to deviate and choose the bottom link, and as I indicated, as long as the traffic on the bottom link is strictly less than half, there's going to be an incentive to deviate, and the incentive is going to stop when the traffic balances out half. At this point of time, these guys, they're experiencing a delay of 1. If this on the bottom link, they still see a delay of 1, so they don't have an incentive to deviate. And the same thing is true of the users on the bottom link. So they see a delay of 2 times 0.5, which is 1, and so they also don't have an incentive to deviate, right? Now let's just to make sure that we understand this. So suppose there's 2 units of traffic, and I again considered the half-half split. So now there's 1 unit of traffic on both the top and the bottom links. Now again, this is not going to be an equilibrium, because on the bottom link, this 1 unit of traffic is experiencing a delay of 2, And so there's an incentive for users here to deviate to the top link, because there, if they deviate, they get a smaller deal, right? So in this case, the split is going to be, if you do the math, it's going to be 1.5 and 0.5, right? So the idea that I'm getting across here is that an equilibrium is where every player chooses a least delay route given what the other players are doing. So if I'm looking at a traffic assignment, that's an equilibrium if every player is choosing the least delay route given the delays that are experienced at this traffic assignment. And if that's the case, no one has an incentive to deviate, and that's why we're calling this a stable outcome of selfish routing, right? So formally, non-atomic routing game is composed of this tuple. So I have this G, which is denoting my directed graph, the network, the road network. I have these latency functions, which are these functions labeling the edges. We're always going to assume that they're continuous and they're increasing, right? So that's continuity is kind of a crucial assumption. Increasing is also necessary for some things that I'm going to be saying. So we'll just assume that throughout. And then there's this there's a source destination pairs, where the traffic is starting and where it's going, and the amount of traffic that's being routed, that's D, right? And we're going to say that a flow of volume D, so a feasible flow sends this D units from S to T, is an equilibrium flow. So formally, what does this mean? It means that if I look at any two ST paths, P and Q, and say that P is a path which has this property that all the edges on P have a non-zero amount of traffic. So I can think of a flow as flows along edges, or I can think of a path decomposition. So this is kind of saying that there's a flow path. P is a flow path. There's some non-negligible amount of traffic going on this path P. So we want to say that these users don't have an incentive to deviate to Q, and that's what that inequality is expressing, that the total delay that is experienced along P is no larger than the total delay along Q. That's what an equilibrium flow is. Right? Any questions? Yes? Okay, good question. So this is not going to be so important for what I'm going to be talking about, because in some time I'm going to be talking about that these functions are not given to us as input. So let me just dodge that question. Okay. When I get to signaling, I'll say a little bit more about this. Right? Okay, so more generally, I could have multiple commodities. So they could be, it need not be that there's just one source and sink. I mean, that would be a little too restrictive if that's all we could model. There could be multiple source sink pairs and different amounts of traffic that needs to go between these source sink pairs, like shown here. And again, an equilibrium. So now the object that we get is a multi-commodity flow. So Fi is routing Di units from Si to Ti. And again, the same sort of idea that we say that something is an equilibrium if whenever I have a flow path, there is no incentive to deviate from that flow path to some other flow path. Right? So this model is a fairly well-studied model. It's been, initially it was sort of proposed and studied in the transportation science literature. It dates back to Waterloo in 1952 and Beckman et al. In 1956. And this equilibrium notion actually, although it looks very similar to Nash equilibrium, it predates that notion of Nash equilibrium. It's called a Wardrop equilibrium due to Wardrop, right? And this is the model that I'm going to be mostly talking about, but I will also spend some time talking about the alternate where I drop the assumption that players control an extremely small amount of traffic. If players control finite amounts of traffic, then we call that atomic routing. And then the different kind of models that arise depending on how players route this demand. So now each player controls a certain amount of demand Di that has to be routed from Si to Ti. And we could say that, okay, this demand has to be routed unsplittably, so it has to be routed along a single path, or it could be routed splittably. You could split that demand as you like across different flows. And you get two models, the atomic unsplittable model or the atomic splittable model for routing, right? Again, the notion of equilibrium is still the same sort of philosophy that each player uses. So now instead of the least delay route, I mean, it's going to choose the minimum delay routing of its demand, whether that's unsplittable or splittable, depending on what the other players are doing. Okay. Okay, so now that we have a model, we can start asking some questions, and these are questions, sort of classical questions that people have asked. So the most basic question is, does an equilibrium flow exist? Question?
Is the splittable case really different from the non-atomic?
Yeah, because so in the splittable case, if I'm controlling, let's say 2 units of demand, right? I'm routing all those. I control how those 2 units are routed, right? So it's subtly different from non-atomic. Yeah. So atomic means that whenever players are controlling a non-negligible amount of traffic, we're going to call that atomic routing. So each player is an atom who is controlling some significant portion of the flow. In the earlier model, each player was just an epsilon amount of flow, right? So, but here, let's say that's a player. So that player, in that example, if that were the player, then the player is going to choose the best way of routing 1 unit of traffic from S to T. Whereas in the earlier non-atomic case, each player is just looking at, each epsilon is just looking at taking the shortest path from S to T, given what the others are. Okay, so, all right, so the first basic question is, does an equilibrium flow exist? And if it exists, is there just one equilibrium? Are there multiple equilibria? Can we compute an equilibrium efficiently? And we can ask this both in a centralized context. Is there a central, I mean, in the normal kind of computer science sense, can I give an algorithm that computes this? Or maybe what makes more sense is that since I can't actually control the players, is there a decentralized algorithm where players are just making moves and that reaches an equilibrium? So then I can ask, so in an equilibrium, again, there's no global objective, right? Now, if I had a global objective in mind, let's say the total delay experienced by all the users, right? Let's call the flow that minimizes the total delay the optimal flow. How bad could equilibria be compared to the optimal flows, right? So, and if equilibria are not unique, then I guess I have 2 possible choices. I can look at how bad is the worst equilibrium or how bad is the best equilibrium, right? And these two, the inefficiency of these with respect to the optimal has been the price of anarchy for the worst equilibrium and the price of stability for the best equilibrium. And finally, if it turns out that, so equilibria are stable outcomes, but they may have some undesirable aspects, right? So it could be, for example, they could be undesirable because they're bad compared to the total delay objective. Or it could be that they're undesirable because of some other external effects. So for example, it could turn out that an equilibrium is routing too much traffic in some residential area or near a hospital or something like that, right? So one can ask, can I find ways to steer equilibria towards more desirable traffic patterns, right? And of course, I mean, I can't dictate the routes, right? So we want to have subtle ways in which we can influence equilibria, right? So if I could control all the flow, then all of these questions become moot, right? But one way of controlling equilibria is that maybe you could impose tolls on edges, tolls on certain roads, and that might influence traffic behavior because now users have an option of maybe taking a faster route but paying a larger toll versus taking a slower route. So there's some sort of trade-off that players have between delays and money, and we can use tolls to influence equilibria and move them towards desirable traffic patterns. Or another option may be, depending on the context, that it's possible that you maybe control a certain fraction of the flow, not the entire flow, but some small fraction, and could you route by controlling some fraction of the total flow, could you route it in a way that steers equilibria into a desirable direction? Yes. So by decentralized, I just mean that there's no sort of central authority that's saying that, okay, this player goes along this route, et cetera, et cetera. It's just there's a system which is the players, and players are just making, think of it as players making best response moves. So right now there's some state, there's some traffic pattern. I'm a user, I see that there's an alternate route that I can switch to, and I keep making these moves, and the question is, does that kind of an algorithm, so there's no one dictating how the players are moving. They're just moving out of their self-interest, and one can ask, is there such a decentralized algorithm that converges to an equilibrium? There are algorithms, there are decentralized algorithms which follow these kind of best response dynamics that in certain settings converge to an equilibrium. Yes.
Whenever we are imposing tolls, are we not going to that centralized info system?
Yes, so we are assuming here that there is a central authority that can do some sort of changes, right? But it's a very limited form of change, and it's drastically, at least it seems drastically less than saying that, okay, I'm going to impose routes on the players, right? And if you think about it, I mean, this is something, well, so this whole area, I guess, arose in the transportation science literature, and there, I mean, if you think about it in the context of road networks, there are these things that happen, right? I mean, tolls do get charged, so that's why this kind of means has been investigated. But you're right that, I mean, we are assuming there that there is a central authority that is computing tolls and imposing those tolls on the edges. Yes. Okay, so let me give answers to these questions. This is sort of classical knowledge, or maybe not as classical for some of these questions, but still well-known knowledge. And for non-atomic routing, most of these questions we have a pretty good understanding of. So for in the case of non-atomic routing, equilibria exist, and they can be computed efficiently by solving this kind of a program. So here this program is optimizing some function of the flow on the edges. These FIs are flows that route the right amounts from SI to TI, and one can show that an optimal solution here is an equilibrium to the non-atomic routing. And actually, that's not hard to see. It just follows from the fact that this is a convex program. So for convex programs, we have nice optimality conditions, and those optimality conditions turn out to coincide exactly with the conditions for Nash equilibrium. Right? And in fact, if the latency functions are strictly increasing, this is a strictly convex program. So there's a unique equilibrium, right? So this is where I'm going to use the assumption that latency functions are increasing. Whenever latency functions are increasing, there's a unique equilibrium, right? So that's great. That's our first couple of questions. And about 15 years back, work by Tim Rafkaran and Eva Tardosh quantified how much worse equilibria could be compared to optimal flows. Optimal with respect to, let's say, the total delay objective. Right, so there's a unique equilibrium, so I don't have to worry about worst versus best equilibrium. There's just one equilibrium, and we know that equilibria can be pretty bad, but we also have, and in fact, we have a precise bound. We have an explicit formula that gives rise, that tells me the price of anarchy, how bad equilibria could be compared to the optimal flows for any class of latency functions, assuming that the latency function satisfies some mild conditions, right? So that's good. Now, what about ways of, so given that equilibria can be bad, it makes sense to think about ways of steering equilibria towards desirable outcomes. And so here again, we have an extremely crisp positive answer that we can efficiently find tolls on edges. Yes? So that's the same as price of anarchy, because in this model there's a unique equilibrium. Right? Actually, and that's true even if the latency functions are not strictly increasing but just non-decreasing, the cost of an equilibrium is always the same. Right? So that whether it's price of anarchy, price of stability, it's the same thing. Okay, so we can always compute tolls efficiently that enforce a given target flow as an equilibrium. All right. So I'll state this more precisely in a bit. So what do I mean by this? So let's say that this is the flow that I wanted to impose. That I wanted to send 4 units on the top and 6 units on the bottom. Now this as is not an equilibrium, because if I look at the delays on the top and bottom links, so these guys on the bottom, they will have an incentive to switch to the top link, right? But what we are saying is that there is a way of computing tolls, a toll tau e on edge e. Now, when I impose this toll, it changes the cost that a user on edge e experiences to the delay that he was placing plus this toll, right? And here I'm assuming that players value time and money equally. That's just for notational simplicity. So if you want, you could add a multiplier there which talks about what's the trade-off between time and money. Right? But let's keep things simple. Let's say that time and money are valued equally. So that's what the net cost a player is going to experience, the delay plus the toll. And so now, given this net cost, players, now we're going to look at the equilibria with respect to that cost, right? So at equilibrium, same principle, players are going to choose least cost paths, and the precise statement is that if I have a minimal flow F star, a minimal flow is a technical condition. It means that there's no feasible flow which is component-wise smaller than F star, and in some components strictly smaller, right? So just ignore this minimal thing. I don't want to define it. Introduce notation to define it precisely, but essentially any target flow can be imposed via edge tolls. So I can always compute tau e's such that when I look at the costs on the edges and find the equilibrium with respect to those costs, I get the desired flow F star as the equilibrium, right? So in this example, for example, what I need to do is increase the delay on this edge to 12. That would make it an equilibrium, so I can do that by imposing a toll of 6 units on the top edge. And then I would get this desirable flow as the right. So with tolls, again we know pretty much what can be done. What about the other options? So let me briefly. Optimal flow is always minimal, right? Because so there is always an optimal with increasing latency functions. The optimal flow is minimal. If latency functions are non-decreasing, you can always assume there is an optimal flow that's minimal. So the other option that I mentioned is that you control a certain fraction of the total flow. So this is called Stackelberg routing. Basically one can think of it as that there's a leader that goes first and routes an alpha fraction of the flow, and then the remaining users, 1 minus alpha volume, comes in and routes selfishly again. So as to equalize the delay. So here our understanding is weaker than with respect to tolls. There are still some questions that are open here, but in sync commodity networks where there's only one sourcing pair, what we know is that we can reduce the price of anarchy, and the precise statement, so for any class of latency functions, you can reduce the price of anarchy, right? There are weaker results known for multi-commodity networks. Now, if I give you a specific target flow, you can find the fraction alpha that you need to control, and the Stackelberg routing that actually yields F star as the equilibrium, right? So this is also a known result. So we know the answers to all of these questions. So now, what do I want to bring attention to? So all of these results. In particular, let's look at the algorithmic results. So there are 3 algorithmic tasks here. There's equilibrium computation. There's finding tolls to impose a given target flow. There's Stackelberg routing to impose a given target flow. Now, all of these results assume that we have explicit, precise knowledge about the latency functions, right? So we know exactly what the latency functions are, and we have to figure out issues like how are these latency functions represented, right? Now, what if we don't have explicit knowledge like this, right? So maybe we don't know the latency functions. Maybe it's hard to determine what the latency functions are, or it may be burdensome to determine what the latency functions are. Maybe obtaining such detailed information is costly, either in terms of time and money, or maybe the only way that you can observe a latency function is by isolating an edge and making measurements along the edge. But if you have a large system, well, maybe you can't do that. If you have a big road network, maybe you can't isolate some portion of it and necessarily measure latency functions, right? So now, what I want to ask is that, do we really need to assume that we have this precise, explicit knowledge of the latency functions in order to achieve these algorithmic tasks, right? Can I analyze routing gains without making this assumption that I have precise, explicit knowledge of the latency functions, which may be potentially onerous to obtain, right? So in other words, what I want to know is that is it really necessary to know the latency functions, or is it just a means to an end, right? So if I look at these 2 tasks, my goal is to impose the desirable traffic pattern, the target flow F star. How I do that is irrelevant, right? So, I mean, do I really need to know the latency functions in order to do this task, or can I get away? Can I sidestep this issue of obtaining information? Can I find other means of achieving that end without actually having the means, right? So I like to pose this as, can we achieve the ends without the means? Right? So that's what is going to bring me to the next portion of the talk, and this is the portion that's going to be one of the new perspectives on routing games. So now I want to look at how can I talk about routing games without having precise, explicit knowledge of the latency functions. Yes. So right now I have no constraint on the tolls. But when I talk about some of the results, I will talk about what happens if you want to impose constraints like that. Well, in the model where we know explicitly the latency functions, we can impose constraints like find tolls that impose this flow F star, and you want to minimize the sum of the tolls. You can do things like that. Okay, so this brings me to the first thing that I want to talk about, which is query models. So here, I'm going to assume that we know the underlying network and the commodities, but I'm not going to assume that we know the latency functions, right? So now, okay, so one can ask, okay, but how are you going to do anything, right? So we have some other way of accessing our routing game. The routing game is given by a black box, and we can query that black box. And in a minute I'll talk about what kinds of queries, what kind of query models one can think about, right? So, but that's the idea. I'm not going to assume that I know the latency functions. We can just access the routing game as a black box. And so now I want to think about algorithmic tasks in this query model. The primary concern in a query model, in these kinds of query models, is going to be the query complexity. How many queries do I need to achieve an algorithmic task? And ideally, I would like to have polynomial query complexity, but also I would like to have polynomial running time, right? So I would also, a secondary concern is going to be computational complexity, as usual when we talk about algorithms, right? So here are some common kinds of query models, right? So the first type of query model is when we have cost or payoff queries, right? So here a routing game is given as a black box, and in this query model, I can input a strategy profile. I can query the black box, give it a strategy profile. So in the context of a routing game, that means specifying a flow. And then the black box is going to give me the costs under the strategy, under that profile. And we can think about different variants where cost means the total cost, the individual player costs, etc., right? But that's the idea. Now, this query model is actually fairly common in empirical game theory. So, empirical game theory talks about if we have answers to such queries, how can I compute equilibria using this kind of query model, right? And there are different variants depending on whether the query, whether you're allowed to give it queries of pure strategies, mixed strategies, correlated strategies, what kind of equilibrium are you interested in computing, pure, mixed, or correlated equilibria. There's a lot of work in this model for general strategic form games, and this is by no means an exhaustive list. But there are far fewer results for routing games, right? I'll mention what is known about these, mention in more detail what is known about in this query model. For now, I want to talk about an implicit assumption or criticism of this query model, which is that if you think about the routing game context, right? So one can ask, well, why is this black box reasonable, right? So I am assuming that this black box can give me the cost for any given routing of the players, right? So, but if I'm assuming that there is no direct access to the latency functions, then maybe, well, to compute these costs, I have to actually route players according to that strategy profile and then measure the costs and measure the delays that are incurred along the edges, right? But that implies that I need to actually dictate routes to players, and that's not the setting in which we are in. So, right? So we are in a setting where there's no central authority that can dictate routes, right? So, I mean, I guess the way to think about this is that, well, this is a reasonable query model in the sense that, well, it is expecting less information. It is, if we are doing things in this query model, we are assuming much less information than actually explicitly knowing the latency functions. We're just assuming this kind of simulation that can actually give us cost. But there are also settings where maybe this is not the right query model, in particular if it turns out that there is no way of actually routing players, dictating routes to players and observing player behavior and observing the costs incurred in that, right? So I want to talk now about a different query model where I don't have this issue here, right? So in this other type of query model, we're going to be talking about equilibrium query. So the black box is going to receive some input, and it's going to tell me the equilibrium flow behavior, right? So here I'm only observing the system at equilibrium. So in contrast to the previous setting, I'm not actually dictating routes on the players, right? I'm saying that, okay, I'm giving it a certain stimulus, giving this a certain stimulus, and then I'm letting the system settle into an equilibrium. I guess I'm assuming there implicitly that there is some process, that there is some simulation that I can simulate an equilibrium behavior. But then, the only thing that I'm going to observe is the equilibrium behavior, right? So this is some work that we did with Umang and Leonard Tillman. This is similar in spirit to what's this a body of work that's called learning from revealed preferences, where again you assume that you have sort of equilibrium behavior in response to certain stimuli. There the goal is to learn some models learn the parameters of some model, maybe the utility functions, or in this case the latency functions, given that equilibrium behavior. Here we don't really want to learn anything, but we want to achieve our algorithmic task, right? If that involves learning the latency functions, then sure. But maybe there's a way of doing it without actually learning the parameters of our model. All right, so I'm going to break this up into two kinds of query models. The first one is what I call is toll queries. So here is a black box. So here the input that I'm going to supply is a vector of tolls along the edges. Right? Again, I assume we know the graph topology, we know the commodities, we know how much demand is being routed, and I get to supply this toll vector. And then the black box is going to compute the equilibrium with respect to these tolls. So these are some latency functions. These are the actual latency functions on the edges, which I don't know about. The black box is going to compute an equilibrium with respect to that. And in this example, that happens to be the equilibrium. It's going to spit out that equilibrium. Right? So the input is a vector, and the output is this is the equilibrium flow. And similarly, I can talk about Stackelberg queries, where the input, I'm going to specify a Stackelberg routing. So in this case, I'm controlling a 0.3 fraction of the flow. So that means I get to route 6 units of flow however I want. So that's what this routing is. And then given that those 6 units are being routed, I have 20 times 1 minus 0.3, 14 units of flow, and that gets routed again selfishly. So because I've already routed 2 units here, if I look at what's the latency that's going to be experienced in the top route, if X additional units are being routed, that's the latency function that I'm going to experience. Because I've routed 4 units of the bottom link, the latency that's going to be experienced to the bottom link if X additional units are routed is 2 times X plus 4. Right? So the black box is going to compute the equilibrium with respect to those latency functions, and in this example, that's what the equilibrium is. It's going to give me that equilibrium. Right? So the common thing across both models is that I'm observing equilibrium flow in response to stimulus. Here, the stimulus is a vector of tolls. Here, the stimulus is a Stackelberg route. Right? And I'm going to focus on the toll query model. All right? So we have, I'm going to talk about some results that we have for toll queries and mention a whole lot of things that we don't know how to do in this model, right? Or various directions that are open here. Okay, so here's the problem formally. We are given some target flow F star, and we're going to assume that it has this technical condition that it's minimal. I want to find tolls that yield F star as the equilibrium flow using these toll queries, and of course I would like to have polynomial query complexity. Right? So that's the problem. Can I do this? Right? And also we would like preferably polytime complexity. Okay, so let me mention the results and then get into details about a specific result. So we have a fairly general positive result that this actually can be achieved in this query model, and that holds for general graphs and general latency functions. And this relies on the ellipsoid method. So basically what this means is that if your goal was to enforce this target flow using tolls, then that task you can achieve without actually knowing the latency functions. All right? So here, knowing the latency functions was really was not really important in the algorithmic task. Right? That's the insight to cull from this. So in this case, some polynomial bounds, and if I specialize the graphs or if I specialize the latency functions, then we can prove some improved bounds. For series parallel graphs and have single coordinate networks but linear latency functions, then we can get improved bounds. The algorithms run in polynomial time, and one subtle issue is that, well, if you have nonlinear latency functions, the equilibrium flow can be irrational, so it doesn't really make sense to talk about a black box that outputs as irrational quantities, again, however they're presented, but we don't really need that. We can get around with just if a black box returns approximate equilibria. And we have some very limited lower bounds in this model, so what one can show is that, so E is the number of edges, that we need at least the number of edges roughly queries in this model. Now, yes? It can, right? Convex programs can be, yeah. Non-linear. Yeah, non-linear, yeah.
Output of the black box is the flow, right?
Yes.
So, but just by doing that, how can I have a handle on how much time it takes? Suppose I'm a transportation agency, so the black box only tells me you send
Right. So maybe what you're asking is that how do I know the cost of the flow that's returned?
Yeah.
Right. So we don't. But the point is that we don't really need that. So our goal is to really impose a given target flow.
That is correct, but as a owner of, let's say, I'm an installation of the owner, so to my customers, they should be able to tell, within this much time, I should be able to deliver your goods.
Okay, so I think maybe what you're asking is that suppose my algorithmic task was different, which is that here I'm saying that I have a given flow f star and I want to impose that. Instead, you could ask, can I actually achieve the optimal flow, the minimum total delay flow, right? So I'm not going to talk about that, but let me just answer your question. So in this model where we have toll queries, where you don't get any information about the cost, that's actually impossible. So this is some work that we showed with Siddharth and Umang, that just if you don't get any information about cost, you can't actually compute the optimal flows. But if you augment your query model to say that you're getting the equilibrium flow and the cost of that flow, then we can actually compute an optimal flow. Okay.
This model again, you are assuming that this latency function, so you don't know that they have all kind of those properties, monotonicity.
Yeah, that's the only thing that we are really assuming. Well, there's that and a few other things that we're going to assume. Like we need to have some sort of information about the bit complexity of this function. So I'm going to assume minimal things like that my latency functions have some slopes which are in some bounded range, and they have I have some estimate about the bit complexity of the numbers involved in the latency functions, right? That's the only thing that we're. I mean, the query complexity is going to depend on that bit complexity. Okay, so now we can ask that, well, why do we just let's try for something stronger, right? Let's actually try to learn the latency functions. So this is the kind of thing that would be a question in learning from revealed preference. You're observing equilibria and you want to learn some parameters, learn latency functions. Okay, so we can't actually learn the true latency function, right? I mean, if I just had a single edge, or if all the flow had to go along a single edge, there's no way I could learn that latency function, all right? There could be any latency function on that edge, and that's not going to affect any equilibrium, right? So, but what we really mean is that can I learn some equivalent latency function? Equivalent means that they are equivalent under your query model. So if you have toll queries, that means that I'm going to say that two latency functions are equivalent if they yield the same equilibrium flow, regardless of what toll vector you put, right? So you can ask, is there a hope of learning an equivalent set of latency functions? Right, so that's the question. Now, I don't know the answer to this. This is I guess this is the first open question. But I think this is a difficult problem. So some hint of that difficulty, we do know that it's computationally hard. So in the computational question, let's say I gave you explicitly these functions, LEs and L prime E's, and we want to know that whether or not they're equivalent. That turns out to be NP hard, and it's NP hard even if these functions actually are just constant functions, so they don't depend on the traffic, right? So here representing this is just representing the numbers, right? So I think this is a difficult task, and so the point is that the fact that we are not actually learning the latency functions is not really a bug; it's a feature. So the algorithms, the positive results that we have are basically showing that you don't really need to learn the latency functions in order to achieve this task of imposing a target flow using tolls, right? In some sense, we are learning just enough about our latency functions so that we can achieve our algorithmic task, right? So this would be great if we could do this. We're not able to do this, but maybe that's for good reason. Maybe that's going to take us many more queries than we actually need. Yes.
Is this question, well formed? Like, are you going to restrict L prime to be from some class? And then, what do you mean by learning a latency function? Be learning the parameters of the function.
Right, so I mean, to make it concrete, let's say I told you that the actual latency functions were linear, and I had I told you that the slopes and the intercepts have a certain bit complexity. Can you, after making some number of queries, give me latency functions in the same class, so linear latency functions that are equivalent in this sense?
So even for linear, we don't know how to do it?
Yes, we don't. I mean, it's open here, but this hardness holds even if just constant latency functions. So it's probably hard. I mean, again, it's open, so this is right now a conjecture, but.
Why do you want this sort of strong notion of equivalence? Like, about just asking the equilibrium flow to be equal
Okay, so my
equivalent under your target flow.
but what does that mean, right? So because the target flow is not really in equilibrium, I have to impose some tolls.
There is a toll at which under both L and L prime, the same toll induces the target F star.
Oh, I see. So you're saying, instead of saying that they give rise to the same equilibrium flow for all tolls, just say that any tolls that give rise to F star under one also give rise to F star in the other end. Yeah, I guess that's a fair question. Yeah, I don't know the answer to that. Yeah.
Once you get tools, you can always reverse engineer to get compatible latency functions. So that's not a.
Once I get.
So I know tolls, I know F star. I can always get compatible latency functions which under the tolls would give me F star. So in that sense,
Oh, right. Okay. Yes. So what you're okay. So what Umang is saying is that if I had that goal, then that's essentially the same thing as finding tolls that will give me F star, because actually, sorry, if I have those tolls, yeah, if I have tolls that I know are going to give F star, I can engineer some latency functions that with those tolls will give me F star. Okay, yeah. So that boils down to the same thing. Good. Okay, so let me give a sketch of this result here. It's actually not difficult. So again, this is the problem. We want to compute this target flow, and just for this talk, let's keep things simple. Let's assume that I'm just going to look at single commodity and linear functions. And let's say, so because I'm assuming that things are minimal, I know that there are always some tolls that impose F star. So I have these tolls tau star. And the only thing that I'm going to use is the equilibrium characterization, right? I mean, in some sense, that's the only handle I have. That if I'm sending a non-zero flow along some path, then that flow path better be a minimum delay path, right? And the idea that I alluded to earlier is we're going to use the ellipsoid method. And we're going to think of it as the ellipsoid method is going to be used to search for this point, which is the parameters of the latency functions and these tolls. So that point, A star, B star, and tau. Right? So let me briefly describe the ellipsoid method. So if you haven't seen this, then this would be a great thing to take away from this talk. It's got nothing to do with routing games or query models, but it's much more useful than that. So here's what the ellipsoid method does. So let's say I have a polytope A, and I want to determine if this polytope is non-empty, or find a point in it. Right? So what we're going to do is we're going to start with a big sphere that contains our polytope K, and we're always going to look at the center of our sphere. So the sphere is no longer going to be a sphere in subsequent iterations. It's going to be an object that's called an ellipsoid, which in 2 dimensions corresponds to an ellipse. We're going to look at this center point. If that's not in our set, we want to have a procedure that tells us that if it's not in our set, we want to find an inequality that's violated by that point. So an inequality that's satisfied by this set but is violated by this point, right? So an inequality like this. I guess the inequality is going to say that it's going to talk about this half space, and it's going to talk about this half space that things should lie. Anyway, so you get the picture. Right? So I want to find a violated inequality, and that's going to chop off half of my region, right? So this procedure is called a separation oracle. And now, once I have that, I'm going to compute the minimum volume ellipsoid that contains the unchopped half. So the unchopped half is the half that contains my the region of interest. And we're going to repeat this. So now my center, that's also not in my set. I find this an inequality that kind of separates this point from this k, and I look at the minimum volume ellipsoid, and I keep doing this. And once I get a point inside my set, I'm done, right? So, and the theorem is that if I continue this process for a number of iterations that depends polynomially on the dimension and the ratio of this radius r, and let's assume that this body k has a ball of some radius sitting inside it, so it's non-zero volume, then that's what the number of iterations that I need. Right? So this is really cool. So what I want to sort of draw attention to is that this is really, I mean, how little information the ellipsoid is using about this convex body K, right? So the only thing that I needed, so think of this is really kind of a query algorithm, that the only thing that I needed is to solve this problem, determine if my point is not in my set, and give a certificate that certifies, give a certificate in terms of an inequality that certifies that the point is not in my set. As long as I can do that, this whole thing works, right? And in fact, I mean, so here I was assuming that there is a small ball inside this, but there's a, so the driver and starting with some work of Kachian, they actually iron out things so that we have a really crisp statement about what the ellipsoid method does. So let's say I have some polytope and it has some encoding size m. And by encoding size, I mean the maximum number of bits needed to represent, it doesn't matter, a vertex or an inequality, a facet-defining inequality of my polytope. Let's say I have a polytope with that encoding size, and I have a separation oracle that, so whenever that point is not in that set, it's going to give me a certificate, an inequality that tells me that certifies that it's not in that set. And I want that the hyperplane, the numbers needed to represent the bits needed to represent the numbers in that hyperplane, they have size bounded by m and the size of the point that's being queried. If I have that, then using a polynomial number of calls to the separation oracle and in polynomial time, I can determine whether my polytope is empty or find a point in that. All right, so this is a really awesome theorem. This is great for proving. This is not a practical algorithm, but it's great for proving theorems, right? And indeed, that's what we're going to do. We're going to use this to prove our theorem. So again, what was the idea? The idea was to use the ellipsoid method to search for that point, right? So I'm going to think about the set, the polytope that I'm searching for, just consisting of this one single point. This point A star, B star, tau star. Right, so it's a very weird application of the ellipsoid method. The polytope is just consisting of that one point. Right, so what do I need to do in order to run the ellipsoid method? What I need to do is, so first of all, the encoding length is some number m. As I said, we need some estimates about the encoding lengths of our parameters and the total. So we are going to assume that encoding length is part of our input. So what do I need to do? I need to do that given a center of my current ellipsoid, I need to be able to determine whether that point is whether that point is actually this point, and if not, separate it from this point. All right, but wait, so this seems like asking for too much, because if I could actually do that, I would actually learn this latency function. And I just said that that's actually, I don't believe that that's going to be doable with polynomial queries and in fact, you can't strictly learn the latency function. You can only learn something equivalent, right? So what do we actually want to do here? So I'm not going to always be able to separate this point from this set K, right? But what we are going to say is that, so this point is already giving us some tools tau hat. And what we are going to show is that if these tools tau hat do not yield the flow that I desire as an equilibrium, then I will be able to separate my point P from my convex set K. And if you think about it, that's enough, right? Given the theorem that we had, that's really what we need to do, because either we already have good tolls, tau hat, and we are done. Otherwise, I'm going to find the separating hyperplane, and then after a polynomial number of iterations, I would have either during those iterations found some tolls, or I would have actually figured out this particular point, A star, B star, tau star.
So it can say where the algorithm calculates whatever could be that A hat, B hat, tau hat, that is in the previous notion of equivalence, that is kind of your equivalence, point to A star, B star, tau star, right?
Yeah, so it's going to be the fact, well, not in the notion of equivalence that I had, but what's going to be true is that those tolls, and in fact even these latency, so what will be true is that those tolls with my true latency functions are going to impose f star. It will also be true that those tolls along with these latency functions impose f star, but that's just something that falls out of the algorithm. But we are not saying that, so I'm not actually, these tolls, but we don't know that those latency functions are such that regardless of what tolls I supply, that they're going to give the same outcome as those tolls with these latency functions, right? So it's not the case that that's going to be equivalent. It's just that those tolls work for us, and those tolls work for these fictitious latency functions. Okay, so let's see how to do this, right? So there are going to be two cases. So one is that let's say that f star was not the equilibrium flow with these latency functions and the tolls tau hat, right? So that's one case. So, but what does this mean? It means that this is not the equilibrium flow. That means that somewhere there is some path P and some other alternate path Q such that f star is routing positive flow along P. But it turns out that the delay under these latency functions and tolls tau hat along P is larger than the delay along some other ST path Q. Right? That's what it means to not be in equilibrium. If the inequality were the other way around for all P and Q satisfying these properties, then that's the definition of equilibrium. Right? So we have these paths P and Q, and we can find that efficiently. That's not hard to actually argue. But we also know that f star is the equilibrium flow with the true latency functions and the true tolls, right? That's by definition. So that means that if I have these paths P and Q, and if I look at the true latency functions, the A star, B star, and the tau star, the tolls that impose f star, then this inequality goes the other way around. And that's it, right? That means I'm done. I have found an inequality. I have found this inequality which if A, B, and tau were A star, B star, and tau star, then this inequality is satisfied. But if A, B, and tau were A hat, B hat, and tau hat, then that inequality is not satisfied. That's what it means to separate. So I've separated my point from my polytope, and that polytope just consisted of this one single point, right? So that's what it is. Okay, good. So in this case, we're done. Yes?
With this previous, for example, even for the case of linear latency functions, is there any kind of a characterization for a given target flow? Can we characterize the space of A, B, and tau so that for all of them this kind of an equilibrium flow?
So I can give a characterization of all. There's a polytope that characterizes all A, B, and tau, such that f star is going to be the equilibrium for that A, B, and tau. So yes, we can do that.
And that will be like the same LP?
Well, I didn't have any LP. Maybe what you're asking is that maybe I should think of K as being that set. Now, I don't really want to think of it that way because I don't have a good handle on the bit complexity of that set. I could make it work using more work, but for me, it's convenient to think of that K is this one single point, and we are either going to have tolls that give us our flow, or separate it, or find an inequality that's satisfied by this point but not by the current point that we have. Yes?
How can we ensure that for some AI dash, and tau dash, this equilibrium condition satisfied, which is different from positional dysfunctions?
Sorry, are you asking how whether f star is an equilibrium for these? Well, that's easy to do, because I mean this f star is an acyclic flow, right? So what I can do is I can look at the longest flow path and the shortest flow path. Because it's acyclic, I can compute both, and I can just check that they're the same delays, and that means it's going to be an equilibrium flow. Yeah, go on. That's fine, but we're not assuming anything. I'm just using two things. F star is not the equilibrium for these latency functions and those tolls, and it is the equilibrium for these latency functions. I mean, it could be the equilibrium for other latency functions too, but we don't care. Oops. Sorry. So now let's look at the case. So we're done with the case where f star was not the equilibrium flow. With respect, I get. Yeah. So right now I actually not use the query model. All right. It's in this case where the other case is when f star is an equilibrium flow for the current point, and here I'm going to use the query model. Right, so what do we do here? So let f be the equilibrium flow when I plug in my tolls tau hat into my black box. Right, so here is where I'm going to be using my black box. And now, okay, so we are assuming that the tolls tau hat do not yield f star. Right, so I know that f is not equal to f star. Right, because by definition tau hat is not yielding f star. Right, so f is not equal to f star. And so, but f star was the equilibrium flow. So f is not, so here is where I'm using uniqueness of equilibrium flow. So if f is not equal to f star, that means f is not the equilibrium flow for these latency functions. And now we do the same trick again, all right? So what I did previously was that I had a flow which was not an equilibrium flow for some latency functions and an equilibrium flow for some other latency functions, and I used that to get my violated inequality. And we're going to do exactly the same thing. Because it's not an equilibrium flow for those latency functions, I have these paths P and Q where the delay along P is larger than the delay along Q using A hat, B hat, and tau hat. But it is the equilibrium flow for A star, B star, and tau hat. So that means that when I look at A star, B star, and tau hat, the delay along P is at most the delay along Q. Right? And again, so that gives me my violated inequality. And that's the proof.
So in terms of actually running this, first you try to find tolls and A hat, B hat, you just simulate it until you get a triple where S star is equal. And then you impose a toll and see what action market does.
Right. Yeah. So in this first case, I never used the black box. As long as this is not the case, we already have a violated inequality. Good.
How do you revise this tau hat in the next round?
So that's what the ellipsoid method does, right? So I mean, once I have a violated inequality, I'm going to compute the new ellipsoid, and I'm going to look at the center of that new ellipsoid.
So here we have to know the F.
Yeah, F star is given to us. It's the target flow that we want.
I don't have a right question to ask.
Okay.
So what if we don't know F star? I just wondering.
Right. So I mean, one question you could ask is that maybe I want to compute the optimal flow.
Yeah.
Right? So so what I said earlier is that with just these toll queries, there's no way of doing that. If you supplement your toll queries with saying that you get the equilibrium and the cost of that equilibrium, then you can do it. And the reason is because essentially you can use this as kind of a value oracle that given a candidate flow, you can use. I mean, you can impose tolls to obtain that flow, and then because your black box also gives the cost of that flow, you have a value oracle, and then you can use results that on optimization that say that how can you optimize a convex function using just a value oracle.
So when you say we cannot do, it means it's open, or we can?
No, it's okay. So when I say it cannot do, it means that it's impossible in the toll query model in the sense that there could be two latency functions that are equivalent, but they have different optimal flows. So your queries are going to be the same on those two things, but the objects that you want to compute are different.
Yeah, because you can actually do something in the market setting. That's why.
Okay.
Take it on.
Great. Okay, so
There's no way to sort of tailor your ellipsoid given that your quality of physics.
no, so I'm relying on this heavy hammer of Groschel, Lavoisier, and Skrimer. So basically they did all the hammering that needed to be done. And
I'm just wondering if you can tailor your updates. Can you tailor it given the fact that your K is
can you do something better than generic ellipsoid? Is that? Yeah, I don't know. I mean, I would suspect not but we have better results not using the ellipsoid method for other classes of graphs. Yeah, so I guess I don't know. My feeling would be that maybe not, but I don't know. Yeah, I'd have to think more about it. Question. Okay, so to summarize what we get for these toll queries using a polynomial number of toll queries, we can find tolls that enforce F star, and some extensions we can handle things like having linear constraints on tolls. We don't really use the routing, the fact that it's a routing game anywhere. So it extends more generally for non-atomic condition games. And the improved bounds are not actually using the ellipsoid, but they actually bring up interesting questions, and we needed to derive new properties, structural properties of tolls and multi-commodity flows on series parallel graphs, and sensitivity of tolls to sensitivity of equilibria to tolls. Right? Okay, so let me say some open questions here. Basically, the open questions have to do with atomic routing games. So recall that this was a model where players control finite amount of demand, and they route their demand. And you can look at either model, unsplittable or splittable model, right? This is essentially almost completely open, right? I mean, non-atomic routing games are also better understood when latency functions are explicitly known. But we have some information. We have a reasonable understanding of atomic splittable and atomic unsplittable games, also in the setting where we know the latency functions. But in this setting, in this query model, we have a rather poor understanding of what can be achieved. So, and in some sense, the one sort of key issue is that the fact that equilibria need not be unique. If we assume that they are unique for all sets of latency functions that we encounter during the ellipsoid method, then you can extend this machinery. But the challenge is that need not happen. And I mean, that's not the only issue. I mean, so because equilibria are not unique, you have to answer questions about, okay, what does it mean to enforce a given target flow? Do we mean enforce it uniquely? If that's the case, then we don't understand what target flows can be induced, even when the latency functions are explicitly given. So maybe that's something that one should figure out first. And also for unsplittable routing games, actually equilibria are not always guaranteed, pure equilibria are not always guaranteed to exist. They do exist if we assume things like linear latencies or all players have the same demand. So I'm okay with restricting to those classes. I think that would still be a pretty good direction to sort of resolve in this query model, right? But these are basically pretty open questions for tool queries. There is a question of tightening the bounds that we have for query complexity. In particular, I think our lower bound is fairly weak. I don't know if a linear lower bound is really the best lower bound that one can hope for. And here is a sort of interesting, more nuanced question in this query model, that suppose I give you a bound on how many queries you can make, right? I'm not just shooting for polynomial queries, but I mean there's some explicit bound, or maybe queries have cost, and you have a budget on how much cost you can spend. Then what can you say? I mean, we don't know anything about this even in the non-atomic setting. So in particular, can we obtain a result that says that that after k queries, you obtain some flow, and there's some nice sort of degradation. The distance between f of k and f star degrades nicely, drops nicely as a function of k. Right? I mean, there are such results known for, I mean, things like online learning, like, I mean, the regret goes down, and it would be really nice to obtain a result like this, right? We have no clue how to do this. Yeah. Over time.
So people, instead of being at 8 in the morning, I think at 6.
Flows over time? Is that? Yeah, it could be. I mean, there is. We haven't looked at that, but I mean, there are definitely selfish routing models that talk about flows over time. It may be possible that. I mean, the questions definitely make sense. Yeah, I'm not.
Because in most of the networks, even data networks, you want
right.
You want load balancing across time as well.
Right. So I mean, static flows are really a first order abstraction or whatever, zeroth order abstraction. Flows over time are a more realistic model. Yeah. So it would be.
Comment. I think maybe already whatever you have solves even this.
Could be. That would be nice. Yeah. Yeah. We'll add another 5 pages to the journal version. Yeah. Okay. Right. Thanks. Okay. So I think I was right when I said that I'm not going to be able to get to the signaling stuff. So I'm not going to. I'm just going to talk about the query models, but because there's some more things that I want to talk about for when we have Stackelberg queries, and when we have. I want to go back to what can we say when we have cost queries. So recall that in the Stackelberg query setting, the input was a Stackelberg routing, and the output was again the equilibrium. Now Stackelberg flows are actually less understood even in the setting where latency functions are explicitly given. So we shouldn't hope to do more than what we can do in that setting. But one thing that is understood is in the setting where we know the latency functions is that, and let's just focus on single commodity networks, because with multi-commodities things are not so well understood even when latency functions are explicitly given. But one thing that we do know how to do is that in the setting where latency functions are explicitly given, is that given a target flow and a fraction alpha that you can control, figure out whether the Stackelberg routing that induces F star, or return that there is no Stackelberg routing that induces F star. That could happen, and so we want to figure that out. So we want to look at that same problem, something that we understand in the setting where latency functions are given to us, and we want to see what can we see in the setting, in this query model setting, right? And the answer is not a whole lot. So the result that we can get is we can solve this problem for series parallel graphs. But that's about it, right? That's about what we know how to do, right? So even with general graphs and linear latencies, I mean, linear latencies seems always like a good starting point. That's also open. So one thing that we do know becomes quite hard in this setting is, again, if you looked at the more taxing task of learning latency functions that are equivalent to your latency functions, and now it's equivalent with respect to these queries, right? That whatever Stackelberg routing, that I say L and L prime are equivalent if they're going to yield the same equilibrium for all Stackelberg routings. Now that I do know becomes pretty hard in the query model. It's we need an exponential number of queries, right? So I didn't know how hard this was in the total query model. I do know that it's pretty hard in the or it needs a lot of queries in the Stackelberg query model, and computationally it is also NP hard. Right? Alpha is explicitly given to you. Yeah. So alpha is the fraction that you are allowed to control.
The bit complexity of alpha appeared
in the input size, so you can take polynomial in that bit complexity. Yeah. Okay, so now let me go back to the first query model, which is this cost queries that the input is a strategy profile and the output is question.
Does everything become simpler if I have like a very small number of queries that I can actually query an edge and figure out what the latency function?
Well, I guess if you could do that, then you're.
I'm not doing it for every edge.
Oh, I see. For a limited number of edges, you could do that. Is that the question?
Maybe logarithmic on the.
Yeah, I don't know, but offhand I feel, I mean, without just thinking about it on the spot, is that, so I'm not sure if log is, I mean, I somehow feel that you may need to query everything, because you could imagine that, I mean, here is your kind of network, you add a lot of junk to it, which doesn't really affect things, and now you have to do this task of, I guess, figuring out which edges to query, right? That seems hard to me, yeah, but no, we haven't looked at that generalization. Yeah, it's another question. Okay, so the cost query model, so here the input is a strategy profile and the output are player costs. So in the non-atomic routing world, we have results for how we can compute an equilibrium using these queries, right? So there are algorithms using regret dynamics and other kinds of algorithms. We know how to compute an approximate equilibrium using these kinds of queries. In the atomic splittable routing case, I don't want to go there because we don't even know how to compute equilibria even when latency functions are explicitly given, right? Although I see that Umang has a paper or a poster that talks about this stuff. So maybe now we can get into this. But this, so equilibrium computation, we don't understand that well, or didn't understand that well. So I'm going to focus on the atomic unsplittable routing, and we are just going to focus on pure Nash equilibria, right? So again, they're not guaranteed to exist, so I'm happy to just assume that we are in a setting where make assumptions that we know that these exist. Right? So again, not much is known. So there is some work on it. There's a paper by Kleinberg et al. But they assume a more generous black box, where the black box not just returns the costs that the players incur under the strategy profile, but also the cost for other unplayed strategies. So the costs of, in the context of a routing game, a path that no player took. The Kleinberg et al. result requires that you know the cost of also unplayed actions, strategies, right? So that's not really in this black box setting. And then there's some work by Fernley et al. They have results for, if I look at single source sync, parallel link graphs, or single source sync DAGs. And that's basically what we know. Now, for those of you who are familiar, so you can think of this as, okay, so why can't I just use online learning techniques, right? So online learning, the sort of generic problem it addresses is that you play an action, you observe the cost of that action, and then you want to converge to sort of the, you want to minimize regret. So you want to converge to the best action in hindsight if you knew all the cost functions up front. Now the challenge here is that what you learn from a query are the player costs, but the equilibrium is not really something that minimizes the player cost. The equilibrium is something that minimizes an alternate potential function. So the feedback that I get is not about the function that I want to optimize, which is what usually online learning kind of tries to do, but it's about a different cost model. And that's where it's not clear how to adapt things like regret learning algorithms from online learning, right? And so let me sort of in the next 1 minute just to point out what is something simple that we let me just look at a simple case here, right? So single source sync pair and one player, all right? So this is really simple, right? I mean, it seems really simple, right? There's only one player. Right, so what does this mean? It means that I want to compute an ST shortest path, and what do I have? I have path cost queries. Right, so this is sometimes called a graph discovery problem or network tomography problem, just fancy terms, but this is the problem. Right? The edge costs are non-negative, right? So I mean the latency functions, I mean they're always non-negative, right? So okay, so here's an algorithm for this. I mean, it has pretty good query complexity, order E queries, order number of edge queries, right? So, and what do? I find basically a basis for the collection of simple ST paths, right? So something whose affine hull contains all the ST paths, right? So I know the graph, so I can do this without making any queries, right? There's 0 queries. Now I'm going to query the cost of all of these paths. And this spans all my ST paths, right? So now I can think of, okay, consider the following LP, find me a point in the affine hull of the paths that in my basis, and minimize the cost. Okay, so now, why can I minimize the cost? Why can I write this? Because I don't really know the edge cost. I mean, I'm really searching for the multipliers that define that express this point F, right? And because I know the cost of all the paths in B, I can write the cost of F. So definitely the optimal value here is at most the cost of my shortest path, right? Because the shortest path is a solution to this. And so now if I decompose my F into, it's a flow, it's an ST flow of volume 1, I can decompose that into ST paths and cycles. At least one of every cycle has non-negative cost, right? Because all edge costs are non-zero. Are non-negative. So I know that one of the ST paths in my decomposition is going to be a shortest path. I'm just going to query all of them, and the best among them is guaranteed to be my shortest path. All right, so very simple query complexity algorithm. But this first step it's actually co-NP hard to find such a set. And that's all I know about this. So it's open to give an algorithm with polynomial query and time complexity here. And of course, I mean, this was a toy problem with one player. More generally, I want how to handle this with multiple players. Okay, so let me summarize. So I talked about query models. I didn't get to signaling, but again, I'm very happy to talk offline about that. So query models are this new perspective on routing games where I don't assume that I know the latency functions that they're explicitly given to me, but instead I have some black box access. And we saw that there are kind of various challenges, new challenges that arise in dealing with this kind of black box query model. I talked about 3 types of query models: cost queries, toll queries, and Stackelberg queries. I mean, this list is by no means exhaustive, right? So there could be other models that make sense as well. So for example, you could consider things like, what if you have a query model where you can pick a player and ask him, is he satisfied with his current strategy profile, or ask him to make a best response move or a better response move, right? The strongest results that we know in these query models are for non-atomic games with toll queries or cost queries. With atomic routing games, we have various gaps in our understanding, and we have quite limited knowledge of what we can do in these query models. And I mean, as the last example showed, that even in the special case of a single sourcing pair and one player, even such a special case, I mean, seems quite interesting, and they're interesting open questions, right? And let me sort of end there. Just let me know if you have any questions. Yeah.
So should that you can deal with also like the case for the oracle, there is approximate equilibrium flow. So can you give more explicit about like what's the necessary technical ingredients? So like you need
Right.
the targets and be vex or something.
No, so we don't need any more technical ingredients for what assumptions we are making on the latency function and such. But maybe what's relevant is that when I say we can handle a black box that only returns approximate equilibria, I need a close enough approximation, right? So if I talk about like epsilon equilibrium, that epsilon is inversely in things like the Lipschitz constant of my latency functions and some other things. So I need a small enough epsilons for. So the same ellipsoid-based machinery works. I mean, there's a little more work involved, but because you're working with approximate equilibrium, but as long as the approximation is small enough, and things go through, and we can also show that it's not unreasonable to expect such small approximation in the sense that you can compute epsilon equilibria. I'm not defining epsilon equilibria differently. I mean, you can think of different ways of defining it, component-wise closeness or other ways, but you can get epsilon equilibria in like time log of 1 by epsilon. I mean, if you knew the latency functions, then there is a way of computing epsilon equilibria in log 1 by epsilon. So even if epsilon is inversely dependent on the Lipschitz constant, it's still polynomials. Right?
Which you get, that I guess depends on those two path P and Q, which discriminate between F star and F being the one being non-equilibrium, right?
Right.
So depending on the and there could be many such combinations of P and Q.
Yeah.
Depending on which one you get, the direction of the algorithm may be very different, right?
Right. So depending on what P and Q you choose, you could traverse different. You could have different trajectories. Yes.
Right. So I probably, I mean that's what it goes back to probably the question which he was asking, that is it really we can say that it is completely independent, the complexity, the number of iteration taken to hit that characterizing polynomial, that polytope, right? Ultimately when it hits the corner point of that characterizing polytope, which characterizes a, b and tau for a given target F star, the algorithm will stop, right? The trajectory which it takes depends on how I select P and Q.
Yes.
So I mean, is there any thought on that? Like, it doesn't matter which P and Q I take.
Yeah, it doesn't matter. I mean, it doesn't matter because the proof that the ellipsoid method works just relies on any separating hyperplane.
Can we improve upon that? I mean, any thought? on, we do little better, because ultimately I have to move tau in certain direction, right?
Yeah, so I mean, I don't know how to use the ellipsoid method to get something better, but maybe, so let me just say one other thing. So it's not the case of what Nikhil was saying is that, okay, we hit this point where f star is in equilibrium, but in later iterations that property we may lose, because I mean, I have no control over, in the generic ellipsoid method framework, where my center of the ellipsoid is moving, right? So I can't guarantee that once I mean, like, it's not that there are two phases. Once I hit this property that f star is the equilibrium for my fictitious latency functions, that stays. Now it could be that, I mean, this is also, I think, what Siddharth was alluding to, that, so it could be that for our specific setting, we may be able to improve upon the generic ellipsoid method thing. That's something that we haven't thought about. So, I mean, it could be the case, but somehow I'm skeptical of that. But as I said, we do have improved bounds not using ellipsoid for some special cases depending on the graph or the latency functions. Right, so maybe to answer your questions, yeah, the choice of P and Q doesn't really affect correctness or the query complexity. Right? Whatever P and Q you choose, we're still going to guarantee this query complexity. Maybe a cleverer way of choosing P and Q might help, but yeah, that seems very hard to prove a result like that.
And picking this P and Q is not that expensive, like, I mean, finding out this?
No, because, I mean, we have an acyclic flow, so I can always pick the longest flow path, and I can always pick Q to be a shortest path. And if there's any P and Q that would work, then this P and Q would definitely work.